One way that you can model electricity flowing through a wire is to show a chain in a tube like this. So let's say this tube is the wire, and this chain is all the electrons in the wire. So for an alternating current, your chain would be moving back and forth like this. So in a real wire, your electrons are just vibrating back and forth. For a direct current like those used in batteries, your chain would just move in a continuous loop like this. This can be used to do work. This model is useful because it lets us actually see the current. The faster the flow, the more current goes through something. But if this works as a good analogy, what if we kept going with this analogy and actually tried to use chains to make a working circuit? Could you even make computer logic gates with a bunch of chains and gears? Well, the answer is yes. This means that technically you could make a working computer using only moving chains and gears, although it'd be a rather large computer. So I'm going to be using this cool set called Spintronics to show you how to make some logic gates and other electrical circuits using only chains and gears. So let's start off with what would be equivalent to a battery. A battery is like an electron pump that moves electrons around in a loop. And our device here has a job to move the chain around. So if I pull this cord, then it moves this gear around. But notice that if I don't have anything connected to the chain, then it just goes crazy and spins really fast. This is because the chain has no resistance. This is equivalent to just touching a wire at both ends of a battery. The current just flows like crazy and gets really hot and heats up your wire and drains your battery. So whenever you have a circuit, you need to put some resistance on the circuit. You can do this by adding an actual resistor or like an LED bulb that has its own internal resistance. So there's no resistance to this. Let's swap it out with this one called a 500 spin ohm resistor. I can feel when I turn this that it has some resistance to it. It's hard to turn. Whereas this one just spins freely. Now you can see I charge the battery, let it go. So with the resistor in there, the electrons are just flowing at a steady rate now. So the battery pumps the electrons around in a circle through the resistor. The resistor keeps the current from going too high or too fast through it. In a normal electrical circuit, when you add two resistors in series in the same circuit, the two resistances add together. And the same thing happens with the chains as well. Two resistors just add together, so this is now 1500 spin ohms of resistance. But this chain analogy quickly runs into a problem when we add something called a junction. This is just where we split the wire so that the current can flow in more than one direction. This happens all the time with real circuits. So what do we do with the chains? It's not like you can split the chain to make it go more than one direction. Well, not directly, but you can actually add a really cool device that keeps the analogy alive called a junction. If the current pushes through one sprocket, some flows out the second sprocket and the rest flows out the third sprocket. So you can push current into any of the three sprockets and it'll split between the other two. So with a junction, you can now make circuits that are in series like we saw before, but also circuits that are in parallel like this. You can see that when you add resistors in parallel, they don't add the same as in series. This one that has the lower resistance has a lot more current flowing through its path, but this one that has the higher resistance has a much slower current going through it. And then the total current passing through it is some combination of both of these. So this is one of my favorite setups because you can see how the current splits apart when you have different resistances and different parallel paths. And then you can see how they add together to some total combination of the total current flowing through it. In fact, I could stop this one completely by putting a lot of resistance on it, and it doesn't change the amount going through this path here. That's exactly what happens in parallel circuits. So now both of these currents are exactly equal, but when I let this go, it's not quite equal to this current. So our chain analogy lives on, and now we can make even more complex circuits. One thing that this chain analogy is good for is showing how voltage is measured. The voltage of a real electrical circuit tells you how hard the electrons are being pushed through the wires. So I can measure this battery's voltage by sticking this device on here. It just has a little coiled spring with a needle. The more torque you put on it, the higher the needle goes. So I can measure the spin voltage of this battery by putting it on here. I add a resistor so that it doesn't overshoot the voltage. So we can see we got up to 6 spin volts here. This device can measure voltage, but since it stores torque, it's the same as a capacitor that can store charge. So both of these are switches that can turn off and on. So I can charge it and then discharge it. Charge it and then discharge it. Now I can use these switches and capacitor/voltmeter to show how we can make logic gates. Logic gates are the fundamental components for how all computers work. Computers work by turning billions of tiny switches on and off in a logical manner. In normal computers, these switches are called transistors, and they're turned off and on using electricity. But in our case, we'll use mechanical switches and chains to do the same thing. So the first switch we can make is the NOT gate. This is one of the simplest gates that just does the opposite of what the input signal is. So there's no voltage here unless I turn off the switch. Now there's a voltage. Switch is on, no voltage. Switch is off, there is a voltage. The next important gate is the NAND gate. In this gate, the voltage is off when both switches are on, but if either switch 1 or 2 is off, then the voltage is on. So let's start off with both off. You can see I get a voltage. If switch 2 is on, I still get the voltage. If switch 1 is on, I still get the voltage. But if both of them are on, then I don't get a voltage. Now we have the NOR gate. The NOR gate is kind of the opposite of the NAND gate. So in this setup, the voltage is 0 unless both switches are off. When they're both off, I get a voltage. But in any other combination, I don't get a voltage. Unless they're both off again, then I get that voltage. And believe it or not, you could build the logic for any computer with these 3 logic setups. That means you could build a real computer that runs on chains and gears. This is amazing to think of, and it might sound familiar to another video I did a while ago about a machine that runs on marbles called the Turing Tumble. This is a device that you can build logic in to perform mathematical functions, and you could technically build a computer that runs on marbles. The Turing Tumble and this set called Spintronics were made by the same company called Upper Story. They sponsored this video and sent me this really cool Spintronics set that I've been using today. This set lets you explore electronics in a really unusual way. It's made for anyone from children to adults. It comes with an instruction booklet with a neat and engaging storyline that lets you follow along a story where you learn the circuits as you go. I highly recommend this really cool set to anyone. If you want to learn more about it, go to upperstory.com/Spintronics or click the link in the description. And thanks to Spintronics for sponsoring this video. And before I end, I want to mention how some people might mention Veritasium's video where he discounts the analogy of electrons moving through a wire like a chain, even though he mentioned that's how he used to teach it. The reason he didn't like this method is because it doesn't take into account the flow of energy through the fields that occurs outside of the wires. But for almost all accounts of electronics that are useful in engineering and science, the analogy of electricity to chains moving holds up really well, and it's very useful in understanding the actual electrical circuits and visualizing how they work. There's a saying that says every model is wrong, but some are useful, and that's true in this case as well. And thanks for watching another episode of the Action Lab, and I hope you learned something, and we'll see you next time.